Hi, this is Andy. Welcome back. Today we'll be covering trig substitutions, which is just another type of trig or integral technique. The first rule of trig substitution is to basically avoid using it because it's super complicated. It has a lot of steps, and it's better if you can solve it another way because it'd be easier, faster, and less time spent on your test. And the main idea about trig substitutions is to use trig identities to rewrite sum or difference of squares under the square root. So what I want you to remember is to know this. Square root, something under the square root being added or subtracted does not equal to them breaking apart. Do not ever do this. It's only equal if they're being multiplied together, and they must be multiplied together as shown here. So the main table that you have to remember for trig substitution is this. So assuming a is a constant, we have this table that shows what substitution to use, and we'll go more in depth with the examples. This is the resub right triangle. You're gonna remember this because at the end you're gonna have theta, which is that, or the angle, and you would have to replace it with the value of said theta, and I'll go more into it in the example. And I'm assuming most of you guys have taken trigonometry or some sort of it, so here's the equations again, just in case you forgot. And yeah, we'll get started. The first example. Okay, so from here, you could see that it's not possible to do u substitution since it would be equal to 2x, and then x would still stay in the integral. So we're gonna pull one of our trig substitutions. So x is first, and then a. So what we will have is x equals a times secant theta. So let's write that down. So now we have x equals a. So the a, as we remember, would be 3 squared. As you can agree here. So 3 secant theta. So now we need dx. And dx, as you see here, equals a secant theta times tan theta d theta. So it equals 3 secant tan and d theta. So we have this new equation. And I'm going to go ahead and solve for the resub right triangle. So pay attention. Okay. So from here, we should break it into the cosine value, because secant is just the inverse of cosine. So if we do the inverse of cosine, I just flipped it. So now we have adjacent hypotenuse. That means for the secant value, this would be the hypotenuse, this would be the adjacent. So to label this, the adjacent value would be 3, and the hypotenuse would be x. And that means doing a Pythagorean theorem, we would get x squared minus 9. So we have this resub right triangle to refer to after we have done the integral. So let's plug it into the equation. So dx equals 3 secant theta tan theta d theta over x is replaced with 3 secant theta squared, and the square root is 3 secant theta squared minus 9. Okay, so let's continue down here. So this equals 9 secant squared theta. And this equals, whoa, that's weird. This also equals 9 secant squared theta minus 9. That was weird. I don't know what that was. From here, you can see that we can factor out a 9. So let's go ahead and do that. Actually, I'll just show it here as a easier example. So we factored out the 9, but you can see, like, you might be asking, like, what exactly do we do with this? Well, if we go back to the trig identity, let's pull the main one, sine square. Oh, not the main one, but like the more important one, because you can find basically any trig identity with this equation. Now we divide everything by cosine to find that that's all squares. Sorry, my handwriting is kind of bad. This equals tan squared theta equals, well, not equals, plus 1 equals secant squared theta. So now you can see the trend. Move minus 1 to the other side. We get tan squared theta equals secant squared theta minus 1. So this actually equals over 9 tan squared theta. So now we can get rid of the square root, and now this equals 3 secant theta. So let's go ahead and replace everything. 3 secant theta tan theta d theta over 9 secant squared theta times 3 secant theta. Okay, so now we can start not secant. Actually, my bad. I'm so sorry. It's tan. I apologize for that. That is my fault. It's tan theta. So tan theta cancels out. 3 cancels out. One of the secants cancels out each other, and therefore it leaves us with the integral of 1 over 9 secant theta d theta. So from here we can see that we could take out the 1/9. So go ahead and do that. And remember that secant is the inverse of cosine. So really we're left with cosine theta d theta. So now we can solve this. 1/9 times sine theta. So here's where the resub right triangle comes into play. So now we have sine theta. So now we gotta find the value of sine theta. So sine equals opposite hypotenuse. So that means it equals x squared minus 9 over the hypotenuse, which is x. So now we plug that back in. 1/9 x squared minus 9 over x plus c. And that's your answer. Okay, second example. I'm gonna let you guys go ahead and try to solve it by yourself, and then you guys can check back with me after you're done. Okay, so some of you guys might have tried trig sub, but remember what I said about the first rule. The first rule is to avoid it. Use other methods before this. So from here, you can maybe tell that you could use trig sub or u sub. I use t instead of u, just in case some of you guys are new, because I don't like u, because for integration by parts, we use u and b, so I just don't want to confuse the variables while I do this. So t equals x squared minus 25 dt equals 2x dx. Move 2 to the other side. We get x dx cancels out, so we get 1. And the bottom goes to t. I'm pretty sure, yeah, t. dt over 2. So now we move it to the outside with the 1/2 and then simplify it down. We get t negative 1/2. Okay, dt, my bad. dt 1/2, which this would equal plus 1, so it equals 2 t 1/2 to the power 1/2 dt. So this would just equal t, or just square root, not dt, my bad, pussy. Square root of x squared minus 25 plus c. And that's your answer. So sometimes just don't do trig sub. Try to recognize that you could probably do other methods before trying that.